In the name of Allah, in this lecture we will talk about corona effect and losses. We always hear about the terms magnetic field and electric field, but what is the difference between the two fields? In a three-phase system, we naturally have three conductors or three phases, and there is always an insulating medium between them. But what happens when alternating voltage is applied to these three phases? Of course, an alternating current will flow in each phase, and there will also be a voltage difference between each phase and the other. From this, we understand that there is the presence of both alternating current and alternating voltage on these three phases. We must understand that the magnetic field is generated due to the flow of alternating current in any conductor or any one of the three phases. This means that each conductor or each phase will have a magnetic field formed around it as a result of the alternating current flowing through it. However, the electric field is generated due to the presence of a voltage difference between any two conductors or any two phases out of the three-phase system. This means that there is an electric field between phase R and phase S, and also an electric field between phases S and T. Therefore, we understand that the magnetic field is associated with the flow of electric current, while the electric field is associated with the voltage difference between conductors or between the different phases. For example, overhead transmission lines. As we can see in front of us, due to the flow of the electric current, a magnetic field is generated around each phase. And due to the presence of the voltage difference between the three phases, an electric field will be generated. It is essential to understand that the air present between the three phases in overhead transmission lines acts as an insulating medium. In other words, air is an insulator just like any other type of dielectric material. Therefore, it is important to realize that air, being an insulating medium, has a specific voltage limit it can withstand. If this voltage exceeds a certain value, the insulation will break down. Specifically, the dielectric strength of air is approximately 30 kilovolts per centimeter, which means that if the voltage between any 2 points in air separated by a distance of 1 centimeter exceeds 30 kilovolts, the insulation will break down, and the air will become a conductive medium. That is why it is necessary to maintain an adequate distance between the three phases in overhead lines. As we mentioned earlier, there is a voltage difference between each phase and the other, and the air acts as an insulating medium between each pair of phases. Let us not forget, as we stated earlier, that due to the voltage difference, an electric field is generated. Therefore, the value of the electric field is directly related to the value of the voltage or voltage difference, especially when there is an insulating medium such as air. Now let us suppose that under any abnormal condition, the voltage value increases. Naturally, this will result in an increase in the value of the electric field. If the electric field increases beyond a certain threshold, the air will no longer be able to act as an insulator. In other words, the air surrounding the conductor will behave as a conductor rather than an insulator, leading to ionization of the air surrounding the conductor or the phase. This ionization of air means a partial discharge occurs in the insulating medium, which is air in this case. As a result, the insulation provided by air between the conductors or between the phases will break down, leading to a complete failure of insulation manifested in the form of a very intense electric arc. For this reason, it is necessary to ensure sufficient distance or adequate spacing between the conductors or phases of overhead transmission lines to avoid such issues. However, we must also recognize that under certain conditions, the electric field within the insulating medium, which is air, may increase, and this increase in electric field leads to the ionization of air, and consequently, the occurrence of partial discharge, or what is known as the corona phenomenon. Thus, we understand that the corona phenomenon is essentially a partial discharge phenomenon in any insulating medium, whether that medium is air in overhead transmission lines or, for example, insulating oil in electrical transformers that insulates between the windings. That is why we observe in overhead transmission lines that the air surrounding or existing around high voltage conductors undergoes ionization, leading to the occurrence of the corona phenomenon. It is important to understand that the corona phenomenon intensifies if the surface of the conductor is irregular or rough. It also increases if the air between the conductors contains moisture or if the pollution level in the air is very high. This is because the insulating capability of air becomes weak due to the presence of moisture and pollution, which facilitates the ionization of air more easily. We must also recognize that during light load conditions, the voltage increases, which means the electric field also increases. Naturally, this increase in the electric field intensifies the ionization of air, leading to the occurrence of the corona phenomenon. That is why, as we can see, it is possible to observe transmission lines appearing as if they are glowing or emitting a luminous bluish light, commonly referred to as corona glow. Along with this bluish glow, a hissing sound can also be heard, which is characteristic of the corona effect. Due to the ionization of air, a partial discharge will occur, which is known as the corona phenomenon in the insulating air. Naturally, on overhead transmission lines, we will observe a bright bluish light accompanied by a hissing sound. Additionally, ozone gas is produced as a result of this phenomenon. This is considered the beginning or the initial stage of the breakdown of the insulating air, or in other words, the breakdown of air as an insulator. It is important to understand that due to the corona phenomenon, significant electrical losses occur, which we call corona losses. These losses manifest as the bluish light and the hissing sound, and they also cause interference with radio waves. All of these effects are the losses resulting from the corona phenomenon. In summary, the main causes that lead to the occurrence of the corona phenomenon are: first, high voltage values, which consequently increase the electric field. Second, reduction in insulation strength, mainly due to moisture and pollution. Third, close spacing of conductors, meaning the distance or clearance between phases is insufficient. Fourth, non-uniformity of the electric field, which is caused by a rough, uneven, or irregular conductor surface. So, what are the solutions that we can implement to avoid or reduce the occurrence of the corona phenomenon? Certainly, there are several possible solutions. First, increasing the cross-sectional area of the conductor, because increasing the cross-sectional area of the conductor reduces the value of the electric field on the surface of the conductor. However, it is important to know that the best method to increase the conductor's cross-sectional area is by using a bundled conductor system. This means, as we see, that the conductor for one phase consists of a group of conductors connected by a short circuit. Bundled conductors can be 2, 3, or 4 conductors per phase, as clearly shown in the picture before us. Consequently, the cross-sectional area of the phase conductor becomes as large as possible, which will reduce the electric field around the conductor and prevent the ionization of air. The second solution is to increase the distance between the phases or increase the spacing between the phases in order to reduce the intensity of the electric field. The third solution, as much as possible, is to avoid high voltages, especially during light loads. This can be achieved by installing a shunt reactor at the end of the transmission line or by installing a corona ring. Thank you for your attention. See you in the next lecture.